Okay, today we're going to be talking about linear momentum. Now, if you've had honors physics with me, we never called it linear momentum before because, well, spoiler alert, there was only one type of momentum that we talked about in honors. Now there's going to be two. But right now, linear momentum is going to be the momentum that an object has when it's moving in a straight line. But what the heck is momentum? Momentum has a lot of really crummy definitions. So, quality of motion is vague at best. But these are basically definitions of momentum that I've found in my travels. Product of mass and velocity. Well, okay, but that doesn't. Why would we need that? Like, we could have the product of any two variables. Why would we need to define it as something else? We got to have like a good reason to want to do that, right? Inertia and motion, it's the least crappy so far. So here, this is my Mr. McQuiston definition. It's basically the measure of how hard it is to stop an object. If an object's not moving, i.e. it's already stopped, the momentum is going to be zero. The more inertia it has, the harder it is to stop it because inertia is resistance to changes in motion. And then if it has a higher velocity, it's going to have a larger momentum because it's going to be harder to stop. Now, the problem with my definition is we can have negative momentums, and a negative momentum doesn't necessarily mean that it's super easy to stop it. It just means it's going backwards. So, first off, it is important to recognize that momentum is a vector quantity. So it's a vector quantity because we want to include directionality. So with a lot of our momentum problems that we're going to be doing, we're going to want to define a positive direction and a negative direction and keep keep the positive direction left to right and keep the negative direction right to left or east, west. I don't care. It's going to change depending on the situation. The units for momentum are kgms. No one ever named it after anyone else. No one said like, oh, they're going to be Galileans or whatever. They're going to be McQuistons. No, it's just kgms. Or sometimes you'll see it written as Newton seconds. And we'll get to why it's Newton seconds when I go to the page that's currently upside down. The symbol for momentum is a P with the vector symbol above it. So it's P because, well, M's taken. Originally, when Newton started talking about momentum, he didn't call it momentum. He called it impetus. So that P is coming in there because of that. So impetus comes from the Latin, basically in petere. I mean, I've never taken one Latin class, so impetere is like ingoing or something. I don't know. You should probably have fast forwarded that part. The important thing is it's a weird symbol. It's a lowercase p, and it doesn't make sense to us because pretty much everything so far has like made sense English-wise. There's other things about like, oh, well, German people, German physicists were using P because, they don't speak English. And all the main physicists back at the beginning of the 1900s had to go to Germany in order to like make it. Anyways, formula is super simple. P is equal to mv. Super easy. Now, real quick, I drew a truck, and I drew the truck's going 2 meters per second, so we can figure out the momentum is going to be 5,000 times 2, 10,000. Good job. Meter kgms. Or if I had a 1,000 kilogram car and it's going 10 meters per second, it's going to have the exact same momentum. So basically, momentum, since it depends on mass and it depends on velocity, we could have a large mass and a small velocity, or a smaller mass and a larger velocity, and still get the same amount of momentum. Or we could come up with, let's say we knew how fast we wanted to have something going. So let's say we were talking about a projectile from a railgun that's moving at Mach 5, so 17,015 meters per second-ish. How big would that projectile have to be mass-wise in order to have the same momentum? Well, if the momentum is going to be 10,000, then we could just do 10,000 divided by the velocity gets us our mass, right? And when we work that out, we're gonna get, it's about a 5.83 kg projectile would get us the same momentum as a car going 10 meters per second, which, 10 meters per second, that's nothing to really write home about. It's about 30 miles per hour, or a truck going 2 meters per second, so you could walk alongside that truck. But that projectile is gonna hit just as hard as both of those. So, hey, back in January, there were 2 satellites on they were in a probable collision course with each other. They were expected to pass within 12 meters. So the 2 satellites were the Infrared Astronomical Survey and POPI-B. So POPI-B was a gravitational survey done by the Air Force. POPI-B had an 8-meter, I believe it's an 8-meter boom that extended out from it. So they're expected to pass within 12 meters. This one's got an 8-meter appendage sticking out of it, that some random orientation that no one knows. People were very worried that these 2 satellites were gonna slam into each other, and for good reason, because, well, they had a heck of a lot of momentum. So IRIS has a mass of about 1,083 kilograms. So, well, that was its launch mass. It's used its propellant. Basically, in 1983, when they were done with it, they just left it up there because it didn't have any more propellant to deorbit, which really would have been nice of them. And it's moving at a relative velocity to POPI-B of 14.7 kilometers per second, not meters per second, kilometers per second. So 1,000 meters per second. So basically, had these 2 collided with each other, there would have been a huge amount of debris created that would basically affect low Earth orbit for years and years to come. And they didn't yet. Something's gonna happen one of these days. 2 large satellites are gonna collide, and it's gonna be a crap show. But we've got more relevant crap shows to us right now. So real quick, if we plug in our numbers here, so what you are gonna find, so we just multiply these 2 together, we get 15,900,000 and some change kgms. So it takes a heck of a lot it would take a heck of a lot of the change in momentum, basically, to stop IRIS relative to POPI-B is a huge amount. So talking about changing momentum, hey, we want to talk about what the change in momentum is. And that's going to be something we call impulse. Once again, this derives from Newton's original wording of impetus, But basically, an impulse is the change in momentum of an object. It's going to work really similar to how work worked. Ooh, that's a great phrasing. So, by definition, we've already got a formula for impulse. It's going to be delta p, because delta's change in, p is momentum. So we can use delta p anytime we want to calculate impulse, if we know what our change in momentum is going to be. The symbol for impulse is a capital J. Ooh, that should have an arrow over it. So, we'll call it Jimpulse, I don't care. The units are going to be the same. So it's either going to be kgms or Newton seconds. Now, when we talk about how we get to Newton seconds, that's going to be where impulse comes in, or impulse is going to be why we sometimes use Newton seconds for momentum. And once again, impulse is going to be a vector. If momentum's a vector, impulse is going to have to be a vector. So real quick, if we're changing an object's velocity, what do we need? Oh, wait. Instead of saying change an object's velocity, because changing an object's velocity is really accelerating, right? So to accelerate, you need a you need a force, right? So impulse is going to depend on force. The longer the force is acting on that object, the greater your change in velocity is. Like, that makes sense, right? If I'm driving my car and I push on the gas all the way to the floor for a second, I'm going to speed up a certain amount. If I do the same thing for 10 seconds, I'm going to speed up a lot faster. I'm going to be moving a lot faster than if I just hit the gas for 1 second. So basically what we're saying is impulse is going to be the force times delta t. If we were talking about this in terms of calculus, impulse is literally the integral of the force with respect to time. But we're going to be keeping forces constant for the most part. So we can write J is equal to delta P, or we can write F delta T. Works all the same. Now, if I have a constant force and I extend the amount of time, that means I'm going to get a greater delta P. So where that would come in is if I'm going to exert a certain amount of force fairly constantly, by doing it, so like I was saying, hitting the gas for longer in the car, I'm going to get a greater delta P. If you're playing, baseball or golf or something where you're hitting a ball or puck or whatever with another object, you're always told to follow through with your swing. When you follow through, you're extending delta T, which means you're getting a greater delta P. So that follow through just basically keeps the force constant longer, which makes it go further. If you ever take a look at, like why a tennis racket has strings instead of just being one big paddle, first off, if it was a big paddle, like a ping pong paddle, it'd be really hard to swing it through the air. You'd never you'd tire out pretty quickly. But the strings are tensioned so that when the ball hits, it actually absorbs the impact, and they act like little tiny springs and actually extend the time. The strings, the mesh strings on that tennis racket act like a trampoline, and it's going to increase the change in momentum than if you just had a paddle where you drilled a bunch of holes in it so that you could swing it through the air just as fast. So, on the other hand, if we have a constant delta J, so let's say we're taking something that's moving at a constant velocity and we're stopping it, by extending the delta T, we basically exert less force. So, you can tell the difference between, spiking your brakes and slamming them down as hard as you can, and easing on your brakes in the car. It's a big difference. Or the difference between running your car into a brick wall to stop it. A lot more force is exerted on your car if you run it into a brick wall than if you use the brakes to stop it gradually. Basically, that's the whole thinking behind, using a airbag instead of just slamming your face into the steering wheel. The airbag increases this delta T, so there's less force on your car. If we're talking about car safety, you've also got crumple zones. So let's see, airbags, increased delta T, crumple zones. So crumple zones are basically places that are engineered to give way when there's an impact, instead of having the whole car just come to a complete stop. So old timers would be like, I used to, cars nowadays aren't as strong as they used to be. Well, really what we have is we have areas that are designed to crumple so that the people inside don't get hurt as much. So yeah, you used to be able to, drive your Cadillac into a tree, and you just had to hammer out some dings or whatever. But you had to wash all the blood and guts out the inside. Nowadays with crumple zones, you have a rigid passenger box basically, and then the crumple zones increase the amount of time, and it exerts less force on the people. Then the other one, the pretty gross story that I like to tell, is the dude who, instead of using a bungee cord to bungee jump, because he was doing it on the cheap and on the inebriated side, he decided to use a purloined utility cable that he found. So basically the stuff that hangs between telephone poles was at a work site, tied one end around his ankle, the other end to a bridge, and that had a very short delta T. He had a very large J, and his foot came off. So bungee cords are another example of there being less force by extending that period of time. You can come up with a ton of examples. The difference between boxing gloves and just bare knuckle boxing, like no one's going to go 12 rounds just slapping it at each other. Even boxers themselves, when they do take a punch, you will notice that they do something called they ride the punch, where you basically follow the punch backwards with your face. So by jerking your head backwards as you're getting punched, you get less force. Sure, you can sit around for the next week watching Russians slap the crap at each other, the Russian slap competitions that we all know and love on YouTube. So that would be another example. Anyways, the cushions and, gymnastics and, Mr. Rogers telling you to punch a pillow, all these things, you get less force because you're extending the time, right? If you're punching a pillow, your hand hits and it's absorbed by the pillow. Okay.